Hello, everyone. Um, I guess we can start now. I hope everyone can hear me. Okay, so this is the week two of the quantum computing workshop. And in the previous week, Nishal has talked about the basics of quantum computing, including the gates and how the basic quantum phenomena happen, including the some sort of physics aspects to it. So in this, we deal with the standard problem of searching. Okay, so searching is obviously there everywhere. Why? Because everything is data. Like I go to some type of supermarket, I go to Minimart, they have data about like what I'm purchasing and what is there in their records. So everything is data, and you can make certain type of patterns with the data too. So let's say someone who buys something like chocos would buy milk. Okay, so this is a type of pattern that you derive from the data of previous customers who have bought it. But to do that, you first need to understand a critical thing called searching. So assume you have like a library or like archives of huge data. It'll get challenging as the complexity grows, and by complexity here I mean the number of books, right? So I need something in which I can maybe sort it out faster or search it up in a quicker way than normal. So in computer science, you might have seen or not seen, doesn't matter. There's this thing called data structures in which you arrange data in a certain fashion so that you can access elements. And one such basic thing is called an array. Okay. So it's just memory blocks that are in a continuous order, but they hold certain type of data. It can be someone's name along with their whole record, or it can be just some numbers or something like that. So if I'm going through an array and let's say I have only three elements, I can easily find out what I want. But let's say I have like hundreds of elements, it'll get harder as the number of input is there. So that's how we deal, and that's how quantum computing has offered us a fast approach, and that's something called as a Grover's algorithm. Now, in normal thing, let's say if I want to find a certain text in a page, you have to go through each one of the page and like you go on searching through it one by one. But quantum computing, since it's faster, everyone has heard that it's faster or it can search faster. It has a algorithm called Grover's algorithm, which offers a faster speed up. And how exactly do we know what is faster? We can't really say that, oh, this takes 10 seconds or this takes 100 seconds, because that is something that's completely dependent on your computer, right? Your hardware specifications. So to do that, we have something called as the O notation that you see. It's called the big O notation. And before we start or start to understand what exactly the algorithm is, let's look at this thing called big O notation. Okay. I hope everyone's with me so far. All right. Perfect. So now that we're talking about time, or like rather how much time any process takes, we need to generalize it, right? I don't want to keep like this takes 2 seconds to take. If I run it in my friend's computer, it may take 1 second. So first thing before we do that is we define what's the amount of input we can have, and that we can't tell because sometimes there might be 10 customers today, there might be 100 customers tomorrow. So we just generalize it with a variable called n, which represents the number of input or number of customers in this case. So the whole measure of Big notation goes on how, even if input grows, how does the whole graphical representation grow? So let's say if n is maybe 10, I take 3 seconds, but if it's n is equal to 100, I might take 30 seconds, something like that. So why exactly does this n or generalizing it actually matter? If I have, as I've said, if I have 10 items here, you don't really need much time to find out like what exactly you need. But if you have millions of records or millions of data, which is very common these days, you actually have to search through it. And the best way is as described in the graph. And one common example is this thing called big O of n, which is the blue color line here. That's what I've written in the example. So, assuming you have to search for someone and the person's name is Aryan, yes? So, we won't know how many Aryans there are until we go to the end of the database. And to go through that end of the database, if there are 10 elements, it'll take 10 iterations or 10 seconds. If we assume that it takes 1 second for every record. Now, if it's 10,000 inputs, then it'll take 10,000 seconds. That's why we write it as n number of time or big O of n. Now, the same thing for the standard case of big O of 1. Let's say you have to find something like 3 plus 2. It has nothing to do with the data itself, right? So it's just a simple addition, and you don't need, even if the input is 10,000, that is not related to the summation that you're doing. So that is what big O of 1 is. Like that, you have logarithmic values which are mathematically derived. Now that you guys have got a simple understanding, I'm assuming you guys understood it. Can you guys react or something? You can always message if you want. If you have a doubt, I'll clear it as I'm teaching. So, if you guys understood the basic gist of this time complexity, we can go to the algorithm part. Now, why exactly I need it? Because I need to prove that my algorithm, which is in quantum, is superior to the classical methods that have been going on for decades, right? So the problem is simple. So assuming that I have to find a single needle out of a whole haystack, that's what is the classic problem of searching, right? Like I have to find one thing out of a lot of things. So you define the problem mathematically, since it's a quantum principle. So if we have to define the size, which is the input, which is what we do always, we usually keep it unstructured because that represents the real life scenario. Because usually in real life, you don't have like a structured record of data. The example that I've given here is phone book with n number of names, and all of them are randomly shuffled. So it can't really be like alphabetical order or something like that, name wise. So you have to search one by one instead of going and randomly finding someone with first letter as S, and then that's a different way of searching it. So, assuming the input size is given, what we have to do is we have to find that one unique element or one unique thing that we have to find, which is one. Like it should return one, all others are zero. So, in simple terms, it's basically like assume you have an um, array like this, but instead of the input being like 2, 4, 10, let's just assume everything is zero and just one element is one, okay, or any number. So the problem is that you have to find that one element, which is what you have to search, okay. So now if we go through it in the classical way, we use this method called as a brute force method, in which we search every single number one by one. We go through it, and Ultimately, it'll take n minus number of n minus sorry n minus one number of checks, because let's say you have three elements, then you'll have to search two times to find out that, oh, it's here. That is on the worst case, assuming that the element is on the last, right? On average, we take n by 2 checks. But even this is kind of bad because we want to speed up things, and quantum computing has a solution for it. What we use is the Grover's algorithm, and we find it in root of n time. So that's a quadratic speed up, right? Mathematically. So by root n, I just mean like, let's say 100 input is there. Grover's algorithm will take like 10 seconds to find it, whereas classical method will take 100 seconds to find it. It's that simple. To do that, we use different gates, as quantum computing always uses a lot of gates. And here the O of F is just something called as oracle, and we define it by ourselves. The remaining is just, as the equation shows, is just if you have a symbol x, you have to find the function such that it's the actual one, like the one that you have to return, the one that you find basically. Did you guys understand the problem statement? Just this is just how searching is. It's just defined in a more mathematical way. That's it. It's as simple as telling that uh, out of all the people in the class, I want to find a person named, let's say, Aryan. That's it. It is just represented in a more mathematical way. That's it. Now, how exactly we do it in quantum is what we're going to discuss. The first thing is a principle that Ms. Charles talked about last week. It's called superposition. So by superposition is just a measure to give of equal results. So every single candidate in the whole list, like shown here, it basically has an equal opportunity of it being the final answer. That's what superposition is. And this makes sure that every single one of it has an equal probability of it getting accepted as the answer. Okay. Now, okay, we put a superposition and we know that any one of it can be. And we have something called as an amplitude here. And amplitude, I've mentioned it, is probability is equal to amplitude square. So assuming there are 1 by n number of probabilistic chances, the amplitude is nothing but 1 by root n. This is just a bit of mathematical concept, but the amplitude here is just used to define the whole quantum gates. Okay. So did you guys understand about the superposition, how it's working? All right. Perfect. So, okay, if you guys understood what superposition is, uh, we can go to the next part, which is something called as phase flip. Now, this is kind of quantum physics phenomena where we flip the target, and this you might have also seen normally in like your electrical concepts, or where you just flip the bits, something like not gates or something. Now, what exactly you mean by flipping the target is that the answer, which is one, the different element, like everything is zero, only this one is one, you just make it a negative. So if it's one, make it minus one. That's simple. It's just that. So to do that, we have like gate, and we just flip it. For all the other bits, we keep it as it is. Okay. So what this makes is, it's just you find out that target is here, but you still can't result it as an output. You can't show it as an output yet because there's still uniform superposition between all the variables. So there's still a possibility of any one of it being selected as an output. Okay. So we need to make sure that we distinguish this negated one with the ones that are positive. Okay. Now, how exactly do you distinguish? Is by using this is the core principle called diffusion, and that's the next step. So, diffusion or diffusing gate that we use here, it's a pretty straightforward step. So, at this part, like before we start the diffusion step, all the states will look like how it's represented. All are positive except one of it, which is negative. Okay. And if we take average of the amplitudes here, we get a result. And amplitude, as I've already told, it's 1 by root n here. And if you just take that value, it's a mathematical principle where you take the mean of it. Okay. Now, what exactly you do is you need to make sure that the probability of the answer which you have, it should get higher and higher while the others get lower and lower. Now, to do this, we just use a simple mathematical formula of 2 times average amplitude minus the a value. It'll result in the same thing, but it increases the probability. And that's the core principle of diffusion actually working here. And I've just given an example of how it would work also for the same question. So assuming you have a negative value, it gets higher and it gets positive. Okay. But if it's same thing with a positive value, it'll decrease. And that's basically the core principle. So there's just higher probability of the actual answer getting selected. That's it. Did you guys get me? Yeah. If you guys have any doubts, you can. How exactly do we find which state to negate? So there's actually here, whichever input, like let's say we're taking an input X. So if it is like 1 or anything positive, anything above 0, that's what we negate automatically. Okay. And if it's 0, we do nothing with it. And this happens through the superposition principle, where all of it, it's a quantum phenomena where you can parallelly execute everything at once. So instead of going through one by one and checking everything, you rather at once check for which is one and then you negate it. All right, perfect. So yes, once you've gotten the one with the highest probability, you just collapse all the other states, and that's it. You found your answer, and that's what is the essence of Grover's algorithm. But this is pretty much the intuition part. Realistically, to code it out into actually mathematically define it, there's more steps. But I've already told that amplitude is 1 by root n, right? And we need root n such increments, and this root n is actually derived back in 1994, and it's just a long derivation, but that's pretty much the essence of Grover's algorithm. So if you just have it, you get the resulting one, which is what you're searching for, the positive value. So uh, on a research level, if I were to talk about it, here they've taken 4 bits, which is 0001, 10, and 11, and they've just defined it in a matrix. Okay, the matrix here is just a 4 qubit matrix, but they've taken it like if it's 00, it'll be like one of it is 1, and then others. It's just a diagonal matrix with upper and lower triangular being 0. Okay. And one of the minus one that we have taken here is the one that we are supposed to use, right? And once we know that, okay, the minus of, we negate the actual target, which is 1 1 get. And then once we do it, we'll just get the matrix again. It's pretty much straightforward what I've told, but in just a more research oriented way. It's just structured more for application based with matrices and all that. And the same thing in quantum circuits where it's pretty much, so here there are n number of qubits, and for each one of it we apply superposition. The h here represents the Hadamard gates, which we've discussed last week, and then you apply oracle and diffuser, and you repeat it like root n number of times, and then the final one is the measurement, which is how you get the final value. uh, do you guys have any doubts? You can ask. Do you guys understand, everyone? Or what about others? Yeah, that's right. That's perfect. So this is Grover's algorithm, and it's just a classic problem of how to, search for something, and it's now being used everywhere for different use cases. There are also like use cases in like data sets and all that, where let's say you have to find like a like let's say you're dealing with electrical power grids, and you want to find the faulty one or something with the lower voltage or something that needs replacement. So something like that would be the perfect use case for Grover's algorithm, because it can achieve quadratic speed up over classical systems. Now, Grover's algorithm is, it just achieves a quadratic speed up. But the next one is called Shor's algorithm, and this is what actually made quantum computing famous. And Shor's algorithm actually achieves a breakthrough in quantum computing, and the whole idea of how quantum computing makes stuff secure and how it can break through a lot of cryptography stuff started with this. Okay, so the basic problem definition of Shor's algorithm of what it solves is as simple as a factoring problem of finding factors. And here, you know how factoring works, right? Let's say a number like 15 is given. The factors would be something like 3 into 5 gives 15, right? It should be prime numbers such that it multiplies to the actual number. And now, for a small number like 15, it's not really that big of a deal. You can easily find it. But it still has a mathematical way of finding it, where you take like a random number between 1 and the number itself, and then you take square and then you mod it, and then you get something called as a period. Okay. So here it's just as it's shown. If you find 2 to the power of 1 mod 15, you get 2, and you get like that a sequence. So when it stops, like 2 to the power 14 exceeds this, and it's equal to 1 mod 15. So by 1 mod, you can pretty much tell that this is where the sequence stops, right? And the sequence stopping part is the number of times the sequence is repeating also. So that is the number 4. And this is basically the mathematical part behind how to find factors. So once you find the period, you have an equation to find the factors, where you take a to the power r by 2 minus 1 and plus 1, and you get the factors. It's that simple. Now, for classical numbers, I mean, sorry, for classical methods, it's not really that big of a deal, but it only matters when the numbers go above beyond the limit, and it becomes like harder and harder. And one such use case is the RSA cryptography, where you have like usually the famous one is 2048 bits of codes, and it's really impossible to do it at the same time. But that is what Shor's algorithm actually solves, and it actually uses the same principle, but here it uses something called as a parallelism, where you run like multiple operations at the same time. So this actually finds the sequence, okay, or the pattern. So once you find like the pattern, that is 2481 2481, you'll get to know that after each four intervals it's stopping. But the four intervals part, how do we know? It's by something called as a quantum Fourier transform. And you periodically analyze each stopping, and then you find the frequency of the pattern. That's how you find the period. Now, this thing, theoretically, it may sound really simple, but the hard part comes when you have to actually build the circuits for it. Now, it's really simple. It's just the classical way of doing it. But the only difference is you apply the quantum Fourier transform in this. Now, okay, you've gotten that, fine. But how exactly do we, model the circuit and code it out is like this. So you have like input gates and output gates, and you apply here u of f literally means the mathematical transformation that's being used here. The 2 to the power 1 mod 15, the mathematical part is being applied, and you have to generate and pass it to QFT and then measure it. It's that simple. Did you guys get it? I can explain again if I lost it. Hello guys. Did you understand? All right. All right. If you got it, uh, it's pretty simple. It's pretty straightforward. Where you just apply different rotations and you can sort it out. But this also brings in another problem as in what it can solve and what it can't solve. Okay. Now, a famous thing is called quantum key distribution. You might have heard of it, or even if you have not, it's all right. It's a simple thing where there's a person named Alice and she wants to send a message to Bob. Okay. But there might be a person spying on the message called Eve. Now, the whole problem rises when the classical systems aren't able to deal with the uh, spyware. Okay. Now, if Eve is trying to get the message that Alice is sending, the system is not secure. And especially because there's like multiple ways of decoding like the existing systems, it's really not safe. And you might have, that's the essence, that's the start of cybersecurity, right? But quantum computing actually solves this problem by getting this thing called QKD, or quantum key distribution. So two basic principles of quantum computing actually. There's something called as the no cloning theorem, where you cannot make a copy of any quantum state. So this means that, like, if I'm sending a message, if Alice is sending a message to Bob, you cannot really clone that quantum state, and you cannot take the message for yourself. Okay, this ensures that there's like privacy between the messages being shared. Another thing is that you cannot measure a qubit without disturbing it. By this, I mean, like, if you want to measure, and measuring actually happens in the state towards the end. Okay. So here, when the measuring actually happens, you actually change the probabilistic distribution between each state, and you're basically disturbing the whole system. So if someone keeps on disturbing the whole system, you can tell that, oh, your message has been breached, or it's being decoded by other people. That way, like, you can prevent it, and you can stop Eve from spying on messages, and by changing the whole system again. Now, what exactly is the principle behind the QKD is that if the person, Alice, she's sending the message, she encodes it however she wants, and she doesn't tell anyone about it. Okay. Even Bob doesn't know how it's being encoded. But how exactly will Bob decode the message again when he gets it? So to do that, he has two bases. Okay, let's say you're using two bases, which is vertical or horizontally or diagonally. This is the just assume it to be an angle, two different types of bases. So they can basically communicate saying that, oh, I've used plus minus 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 plus, and Alice would tell, oh, I'm using plus 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 minus plus minus. Now these are random numbers. No one knows what it is. But they would know what it is, just Alice and Bob. And when they match the bases together for each bit, then that'll result in some encrypted message, which can get when it's decoded, it makes a meaningful message. And if, let's say, Eve is spying on your messages, and he actually disturbs the whole phenomena, then that will result in a different output, different non-meaningful message, and that way Alice and Bob will immediately know that someone's spying on them. Did you get it? There's a one thumbs up. If you guys, how does Bob know how it's encoded? Okay, so this is the actually interesting part. So let's say there are random numbers, some random sequences, like plus minus plus plus plus, or anything that Alice has used. Okay, let's say Alice has used something like this. Then Bob's thing is to, he gets the encryption, and he gets which bits it goes for also. But he doesn't have to reveal the which bit it is for. He might get a different encryption, like minus 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 plus minus plus. Okay. So if he gets something like this, then he has to match the ones that are actually successful, and he'll get something like this as the result, which may be meaningful in their own context. And that way they can decode and make meaningful sentences. Did you get it? Guys, does anyone else have any questions? You can ask them in the chat if anyone has questions. Right, perfect. Um, that's pretty much the essence of both the algorithms, but that's not it. We'll also be discussing about project that we'll be doing on quantum. So we've just given quantum computing on a small and easy way to understand it, and we've just talked about like two different algorithms, which is the problem of searching with Grover's algorithm and Shore's algorithm, right? Now we wanted your opinion on what you guys want for a project. So we have multiple options that we can choose from, and we wanted to keep it as realistic and as meaningful it can be. So do you guys want to do something like so we have planned out two projects for the next week. Okay, sorry, for the next week. So there's 2 more weeks for the month, and we were planning next week there'll be one project, and next week one more project. So do you guys want to do a project in something like Grover's algorithm or something simple like this, or do you want to do something which involves more of um, machine learning or quantum machine learning? We'll be making polls and okay, all right, perfect. We'll be making polls of the ideas that we have, which we have implemented, and something that's actually easily implementable. If it's quantum machine learning, that's perfect. So we have like multiple ideas. One is with like medical data set and medical imaging and all that. One is like a vehicle routing problem where you actually simulate the whole grids, and one actually is about, it's too advanced, but it's about like quantum reinforcement learning and all that. So we'll make a poll for you guys in the group, so check that out, and you can give us any feedback or reviews about what exactly you want for projects. And we, since quantum computing is really like, hard to begin with as a big, it's really hard to understand as a beginner. We thought that the best way to go about it is not to teach a lot of theory, because that's also too much, like it gets a bit too much. So we'll teach hands on, and we'll go about it. Okay, all right, that's it guys. We'll send you polls today about what the ideas are, so you can just vote out and uh, let us know what you want. Okay, it's perfect. Thank you everyone. Yeah, don't worry. We'll be going through the codes by explaining it properly. We'll also make like proper documentation marked down for it so that you guys understand it. And we'll do live coding so that, it's not really hard to get it, because you really have to go about the whole gates part and all that. So we'll help you out. Don't worry. Yeah. Also, if you have any more feedback like this, you can always mention in the group. All right. Perfect. Thank you, guys.